Hello, and welcome to this video about the total probability theorem. This problem is essential for this unit and usually will be applied in combination with the Bayes theorem. In this theorem, for the presentation of this theorem, we will consider that there is an event and we know the marginal probability of this event. We will refer to this event as event A, as it is shown there in the slide, and we will study the probability that this event happens combined with other events that are mutually exclusive. So as you see in the slide, there will be other events such as B1, B2, Bk. We are referring to K events, but we could be talking about 3 or 4 or 5. So you could imagine, for instance, one event A, which is the probability that someone who has been selected randomly usually rides a bike on a daily basis. And this would be the event A. And we are studying the probability to find someone randomly selected across a population of children, could be, or a population of adult people, or maybe some elderly people. So the probability to select randomly someone who usually rides a bike may depend on the population where we are extracting the sample. And this is the situation that we are going to study. And you could extend this example to other context, to other environment, such as, for instance, having smoking habits among different group ages, or could be the probability to find a defective piece among different populations of providers or suppliers. There are many examples that match with this structure. So there will be a common event, which is A, and this event is interesting for us for any reason for the research, and we are studying the probability to observe this event among each of the groups that are defined in the partitions B1, B2, B3. In this example, K is 3, because we have just 3 partitions, 3 mutually exclusive events. So this law tells us that the probability to observe the event A, the event that's interesting for us, in our example, the probability to ride a bike, is defined as the joint probability, the intersection between A and B1, as it is shown in the formula here, and also probability of A and B2, and we may continue this expression until we reach probability of A and B key. In other words, if you consider the schema we represented on the slide, we are considering the intersection of this area, this section of this ellipse, with this partition, which would be the area, would be the marginal probability of B1. And of course, the intersection, the joint probability between A and B1 is this section here, this section of the shape that's in the middle. It's a common area to both events. And something similar happens with the second event. The intersection between A and B2, of course, is this area that's defined by these straight lines here, this one, and these round lines that came from the shape of the ellipse, and so on. So the law tells us that the probability to observe the event that's interesting for us, the probability to randomly select someone who usually uses the bike for driving, for riding the bike, can be computed as the joint probability of finding someone from different ages, so the probability of being in B1 and also riding a bike, or B2 and also riding a bike. So this is how it works. This is how the total probability law is defined. But also, if you remember the relation between the joint probability and conditional probability, you know that each of these terms that are defined as joint probability can be extended as an expression of the marginal probability of B1, B2, B3, that means marginal probability of being less than 18 or being between 18 and 35, it's not defined, it's just for the example. This marginal probability to belong to each of these categories per multiplication probability of A given B1 or probability of A given B2 and so on. So you can develop this expression having in mind that you can apply this same expression as probability of B1 per probability of A given B1 plus probability of B2 per probability of A given B2 and so on. And this is how we can apply the total probability law. To make the understanding of this law easier, we are going to review this example. Imagine that we have a group of 30 students from computer engineering, and each of them has a tablet, and this tablet come or are distributed according to different brands. So there are some students that have this brand, the Samsung, and there are other students that have Zira, and the rest of students are PH, of course simulated brands. So half of them, about 15, have this brand, and also 10, and also the rest. And then we have some additional information that is represented as conditional probability. So we know that the Zira tablets were purchased online, and that means that among all the Zira tablets, 30% of them were purchased online. The event that's interesting for us in this example is being purchased online. So here we are given information about probability of A being purchased online, given that we know that the brand was Zira. Or for instance, here this 20% means probability of A being purchased online, knowing that 20% of computers were Samsung, and so on. So, knowing this information, we need to answer this question. If one tablet is randomly chosen, what's the probability of not having been purchased online? This is the question that we need to answer, and to do so, first of all, we will convert. It's very important that we translate the information that was given in the description of the problem into numbers. So first of all, we know that if the group has 30 tablets and 15 out of them are Samsung, then it's easy for us to compute the number of tablets that are brand Samsung or brand Zira. So, according to this information, which is just very basic calculations, we can define the events. And this is very important. This line that's here, it's very important for the resolution of any problem about probability. So first of all, you need to define your events. And to do so, you should use capital letters, and you are not forced to follow this notation A, B, C. You can define your own events as S is Samsung, and C is Zira, and PH is PH, and O is online. So choose the letters you prefer, but you need to choose the letter you will use for each event. If not, it's very easy that you will have mistakes in the application of the formula. And also, you need to prepare a good answer, well prepared with accuracy, telling me which is going to be the notation you are going to follow. So, once you have defined the events, which is here in this line, then you will be prepared to compute marginal probabilities or conditional probabilities. In the end, you are translating the information in the problem into data. So what we know is that the probability of S, which is here, is 0.5. Probability of Z will be a third, like 0.33. And probability of PH will be 0.167. And also in this line here that you see, these probabilities are conditional probabilities. So that's the probability of purchasing online the tablet given that it was S, Samsung or Samsung. Probability of online given that it was Zira, probability of online given that it was PH, and so on. So if you apply the formula, you can obtain that the probability of purchasing the computer online will be the joint intersection between online and Samsung plus probability of online and Zira plus probability of online and PH. So you can just add these probabilities and also consider the addition of these three. And with this, you will obtain the probability of purchasing online the tablet. To obtain the probability of not having purchased online, which is the question that we need to answer, you should compute the complement of O. That means probability of no O, which would be probability of O with the bar. And this is something you could compute, and I invite you to compute it because it's very easy. This probability of no O would be 1 minus 0.73. So it's going to be 0.27 or something. So be aware that we can apply the formula to obtain a probability that allows us to compute or to obtain other probabilities. This problem could have been solved converting each of the data into not online, again and again. But it would be more complicated. It's better for us, it's better for our resolution to solve the problem directly with the data we were given, and once we have some general result, trying to convert this probability into the probability of not being purchased online. So when solving the problems, you need to practice a lot, but also you need to have some strategy, some procedure that you are going to follow, and you have an idea of which is going to be the next step, until you arrive to the response that was defined. It's not only a question of combining numbers and obtaining ratios and obtaining 1 minus and so on. You need to think about the strategy and then think about the correct response. So with this, I finished this presentation about the total probability theorem and the example. I hope you find it useful. Thank you for your attention.